Okay, this is 5.7, the last section of Chapter 5, Logistics and Gompertz Functions. 5.7a is what we're doing here. And what we're doing is looking at what happens when there is growth or decrease in, which we call logistic decay, in a certain situation. Now, a lot of times what happens in growth is that, like the example of the book says, we may have some students that come to campus and a couple of them get the flu, and as they start passing it around, then it gets bad, worse and worse and worse. But then slowly it starts tapering off again and people don't keep the flu. So we get this S-shaped curve that looks like that. And the same is the case when there is a logistic decay. So let's say that you have this product that's coming out, and maybe sales start really, really well, but then all of a sudden people figure out they don't like it anymore, and it goes down to only a few people end up liking it from then on. And so that is a logistic decay rather than any type of logistic function that grows or increases. So that's what we're going to talk about today. And there's a couple formulas that we're going to look at. And one has to do with the logistic growth. And that formula looks like this. You should feel really smart that you can solve these things with these crazy formulas. Okay, so there is your growth function. And one of the things that's important is there is called an upper limit. So when we have our graph here, and let's do this in blue. Let's say that we increase and then we taper off. We have an upper limit that is right here, and it's actually a horizontal asymptote. And it means that this blue line will never cross the red line. You'll never sell any more than that, or you'll never grow any more than that. It's used sometimes to discuss if a cruise ship were to crash on a deserted island and there were 1,000 people left. At what point would the population on the island find a place where it never grows anymore? Like all of a sudden, over the years and years of time, the food, the sustaining ability of the island will only allow, say, 10,000 people there. Anything over that will not exist. So that ends up being a limiting value or an upper limit because the line is never crossed. Okay? So things happen. They also say that that'll happen with the Earth, that once we hit a certain population, 9 to 10 billion, it won't increase anymore. It's not like we're going to be overpopulated, not able to sustain the population. We just won't have any more population. Not sure how that works, but that's the thought. Okay, and this upper limit is when y equals c. Okay, so horizontal asymptotes are going to be y equals 0 and y equals c. So whatever number c is going to be that point right there. All right, so let's get started on some of these and see what goes on. Now, example A, they give women in the workforce, and they're looking at some information there, and you're just going to use your calculator in order to figure this out, because A is saying create a scatter plot of the data. So you're going to take that data in table 5.26, put the x values of the years in your calculator, and your y values are the women in the workforce. You're going to come up with a scatter plot of that data, and you're going to find a function of that data, which they give it in the solution part of B that your calculator will find for you. It will give you the A, B, and C values, and then you'll just plug them in to this formula right here. And you will have the logistic function that models the data in the solution section of B. Okay, so I'm not just leaving you on your own in this lesson. We are going to do some examples, but so far there's really not a whole lot going on that you can't just plug some numbers into your calculator. All right, so that is all our logistic growth function. Now if we look at the logistic decay function, where things decrease rather than increase, where demand decreases instead of increases, you'll notice that your horizontal asymptotes are the same, y equals 0 and y equals c. It's just the graph goes the other way. And the equation that you use for this is the exact same equation. It's just, if you'll notice, the A is greater than 0 for both the growth and decay, but the B is greater than 0 in the growth, and the B is less than 0 in the decay function. So just something to keep aware of there. When you're looking at numbers that you end up plugging in, it doesn't change the formula, just changes the numbers. Okay, so if we were to look at the example 2 of expected lifespan, we've got data from 1920 to 2020. So over a course of 100 years. And what we're doing is taking this formula that they give us and understanding what they're asking you to come up with is sometimes good. I remember taking math courses where I could do the work. I just didn't know what the work meant. So hopefully I can explain what's going on here. All right, here's the formula. Okay? So basically, this is the formula that I'd given you earlier. Let me give it again. Y equals C over 1 plus A e to the negative bx. Okay, so that being the case, we know what our b is. We know what our c is. So remember, c is the horizontal asymptote. It's the highest it's going to go. Okay, and in this case, our b is right there. It is greater than 0. The negative is not part of the formula because notice there's a negative in front of the b. Okay, so the b is positive. This negative is this one. It's not part of the b itself. All right, so let's look and see what we've got here. It's saying use this model, use this equation that we have here to determine when you have to be born in order to have a life expectancy of 79 years. So, for instance, the answer to this problem is 121. That means 121 years, or approximately 122 years, after the beginning date of this, we'll have an expected lifespan of 79 years. So if the answer is 121, 122, in 2021 or 2022, people that are born there will have a lifespan of 79 years. All right. Oh, and x, I forgot to tell you this. X is the number of years from 1900. So that's why when I said 121, 122 years, you add it to that to get 2022. So that's when the kid has to be born in order to have a lifespan of 79 years. Okay, so let's go ahead and do this. So we're getting the answer of 122 when we do this math. So kind of going backwards here, but I just wanted to explain what we are looking for. Part A is giving you an opportunity to use your graphing calculator, plug in this part of the equation, and you'll get the answer here. Part B is asking you to do it algebraically, and so that's what I'm going to focus on here because I want you to see what's going on here algebraically. All right, so y is actually going to be 79. So 79 is what we're looking for. A lot of decimals and junk in here, isn't there? All right, so there is my formula for this. So what do we do with this? We multiply both sides by the denominator and then solve for e to the negative 0.024x. So that being the case, we're going to take this, multiply both sides by this. Okay, so not much went on there. I just moved this stuff over. Now the next step is to distribute. So I'm just multiplying 79 times this here. And the e to this power is going to stay the same. Okay. Now, let's subtract this from both sides. So really what we're doing here is just some simple basic algebra here with a lot of decimals and other junk kind of thrown in there. Okay, so really what we're trying to do is we're trying to, so you know what direction we're going, isolate this here. Because when we isolate that, then we can take the ln of both sides and it makes life so much easier. So we're going to have e to the negative 0.024x equals, we're going to divide both sides by this. And in fact, let's just write it that way. Now I'm just following what the book's doing. I would do it a little bit different, but I mean, it's not like the book's doing it wrong, obviously. Okay, so we get that. I would go ahead and divide those two, but it's having you just take the ln of both sides without dividing those out, which is fine. Doesn't really matter. And when we take the ln, we've got this here that goes away, if you remember from other lessons. So we have just 0.024x equals that. Okay, so at this point we're going to divide, which I'm just going to use black here. Divide by this here. And then that will give you your x, which is going to give you a number around or close to 122. And if you remember, it said that x is the number of years from 1900. So we just found x. That's the number of years from 1900. So 2022, all those babies born will have an average lifespan of 79 years. Okay, so that's what's going on with that example algebraically. In example 3 is exactly the same. They give you the data, the table there, and ask you to do the scatter. Then they ask you to do it with a graphing calculator in order to figure the things out. Remember, part E, what is the upper limit on the annual decrease? The upper limit would be C. And if you look at the formula in the solution for B, the value for C is 30.298, so that would be the upper limit there. Okay, so anyway, other than that, it's pretty self-explanatory, bringing us to Gompertz function. All right, so Gompertz function can be a little tricky and can look a little out of control scary because it has this, which isn't too bad. Then it has an exponent with an exponent. Okay, I don't know what that's called. I don't know if it's called a double exponent or what it's called, but I'm going to show you what to do with that. And we're going to look at example 4 with the deer population. And what the Gompertz function does is that it models rapid growth that eventually levels off. Okay, so it can be used to describe human growth, animal growth, that kind of stuff. So there's our equation there, and let's go ahead and look at deer population in example 4 in the next video.